today's goal of this lecture. In my previous video I had seen Schwarz Lemma and Schwarz Lemma. I had seen Schwarz Lemma is when f defined from b01 to b01, which is holomorphic function or analytic function. Holomorphic and analytic actually same. With the condition f of 0 equal to 0, then absolute value of fz less than equal to absolute value of z. Second, absolute value of f prime 0 always less than equal to 1. Furthermore, if equality holds for some z or equality holds in 2, then fz equal to cz for some c with the condition absolute value of c equal to 1. I hope my all viewers have understood. And Schwarz Lemma is, if f of 0 given, then we can find always f of a. And by Schwarz Lemma, modulus of fz always less than equal to modulus of f of 0 plus modulus of z divided by 1 plus modulus of z times f of 0, where given f of 0 equal f of 0, then by Schwarz lemma we can find by this lemma any f of a if f of 0 is given. Also, if f of a is given, then by Schwarz lemma we can find f prime a, which is equal to absolute value of f prime z equal to less than equal to 1 minus modulus of fz whole square divided by 1 minus modulus of z square. And in my previous video I had seen this example. Here given f defined from disc to disc closure with the condition f of 0 equal to 0. We have to find at first f prime 0. In my previous video I had seen f prime 0 is equal to half. This is true because by Schwarz lemma, since f of 0 equal to 0, also by Schwarz lemma f prime 0 always less than equal to 1. Since half less than 1, so f prime 0 equal to half, this is possible. Also, since f of 0 given, so we can find f of 1/3, and f of 1/3 is f of 0 plus absolute value of z divided by 1 plus f of 0 times modulus absolute value of z. Since f of 0 equal to 0, so this value would be 0, and here we have to find f of 1/3. So, here absolute value of z, here the value of z is 1/3 divided by 1 plus 0 times 1/3, and this value would be less than equal to 1/3 after putting. And this is less than equal to 1/3 in my previous video I had seen, but 1/4 always less than equal to 1/3. So, option 2 possible. And I had seen in my previous video f prime 0 equal to sec pi over 6, which is greater than 1. So, this is not possible, and this is greater than 1/3, so this is also not possible. But today's actual question is same type of question, but only the option is defined. Here f defined from disc to disc with the condition f of 0 equal to 0, then option A imply absolute value of f prime 0 equal to 1. By Schwarz lemma, f prime 0 is less than equal to 1. Equal to 1, this is not possible. But here given absolute value of f prime 0 equal to 1. Always 1, this is not possible. It can be. It may be less than 1. So option A is not right option. Second, notice here given, and fourth option, notice absolute value f prime z 0 less than equal to half. That means here the upper bound is half, but by Schwarz lemma this is less than equal to half. Here given f prime 0 equal to half, this is maybe possible. So this is the right option, but here given less than equal to half, that means here upper bound is half, but by Schwarz lemma this is always less than equal to 1. So option D is a wrong option. And B and C, f of half less than equal to half, and C imply f of half less than equal to 1/4. And option B and option C imply f of half less than equal to half, and option C imply f of half less than equal to 1/4. Option B is a right option, because by this I have got f of half less than equal to half. So option B right option, but option C not right. Here since here less than equal to in the question indicate f of half less than 1/4, then this is possible, because f of half less than equal to 1/2. So less than 1/4, this is maybe possible. But here given f of half less than equal to 1/4, that means here upper bound is 1/4, but here upper bound always half. So this is not possible. I hope my all viewers have understood what is difference between this question and this question. F prime 0 less than equal to 1, this means here always upper bound. Here indicate upper bound, here upper bound is 1. F of half less than equal to half means here always imply upper bound is half. But if we consider this option also right, that means here the upper bound is 1/4. This is not true. Okay. I hope my all viewers have understood. Okay. Well, my next example, this is very interesting. DB unit digits in complex number, and G, which is defined from D to D, be a holomorphic function with the condition z0 equal to 0. At first I will see about the G function, then I will see about H function. Since G satisfy all property of Schwarz lemma, so obviously G prime 0 would be always less than 1, strictly less than equal to 1. But here given absolute value of G prime 0 greater than 1, this is the wrong option. Okay. We all of us know, since G0 equal to 0 given, so we can find any G of A. So here G of half would be, if G0 means 0 plus mod z means half, divided by 1 plus mod z means half, and times mod z0, this means 0, and this value would be half. That means, and this is less than equal, G of half less than equal to half, this is right option. And option 1 and option 2. Option 1 imply H is holomorphic function. Since G is holomorphic, so since H is defined Gz over Z, that means obviously this function is holomorphic function, since G is a holomorphic means analytic, since G is holomorphic. And we all of us know Z is holomorphic function, means analytic function, so their division means gz over z would be holomorphic. So here az equal to gz over z, this is when z not equal to 0. So g is here az is holomorphic on all z omitted with 0. Now I will see, is az is holomorphic means analytic at the point 0? At first we have to find is the function is continuous at z equal to 0. That means we have to find limit z goes to 0 az, and this is equal to limit z goes to 0 gz over z, and this is the L'Hospital rule, 0 over 0. So we can apply limit z goes to 0 by L'Hospital rule g prime 0 g prime z over 1, and this value would be, after putting limit, this value would be z prime 0. That means limit z goes to 0 az equal to z prime 0. In this function also defined z equal to 0, at z equal to 0 the value is z prime 0. Since the limit exists, that means the function is continuous, and since the function is continuous, so obviously this function be differentiable because g is holomorphic function. So this function is holomorphic on whole D. So option 1 is a right option. A is a holomorphic on whole D. Option 2 imply if A is HD content D closure. Let's check it. AZ means GZ over Z. Z. And since G satisfies all condition of Schwarz Lemma, so obviously mod GZ less than equal to mod Z to the power n. So absolute value of AZ would be modulus of Z to the power n over Z. So this value would be Z to the power n minus 1. Okay, I hope my all viewers have understood. That means absolute value of AZ less than equal to Z to the power n minus 1. When Z tends to 1, so this value is less than equal to 1. So since absolute value of AZ less than equal to 1, that means AZ contain D closure. So AZ contain D closure, this is also right option. I hope my all viewers have understood all option. Okay, well. Next question, let F be holomorphic function on the open disk such that modulus of Fz less than equal to 1 and G defined from D to complex number such that Gz equal to Fz over Z. If Z not equal to 0 and when Z equal to 0, then this value is F prime 0. Obviously, earlier example and this example is same. Only difference, in earlier example, Z0 equal to 0 has given, but here Z0 equal to 0 has not given. Okay, that means here break the condition of Schwarz Lemma, because in Schwarz Lemma F0 equal to 0 always given. For this, at first see the option. G is holomorphic, absolute value of Gz less than equal to 1. Option 3, absolute value of F prime Z less than equal to 1. And option 4, f prime 0, absolute value of f prime 0 less than equal to 1. At first I will see, is modulus of gz less than equal to 1, where gz equal to fz over z when z not equal to 0. By maximum modulus theorem, since fb analytic function means holomorphic function, by maximum modulus theorem it has a maximum value on the boundary. That means, and the idea is, if dr equal to set containing z such that modulus of z less than equal to r, this is actually the closed digits of radius are centered at origin, then maximum modulus principle imply that for r less than 1, maximum value of this function exists only the boundary by maximum modulus principle. Then given z belongs to d of r, there exists zr on the boundary of d of r such that modulus of gz which is less than equal to, since zr means the points on the boundary, obviously this is less than equal to absolute value of gzr, and which is equal to fzr divided by modulus of zr, and this value given fz less than equal to 1, so this value would be less than equal to 1 over r, and as r goes to 1, then this value is less than equal to 1, and this is true for all z belongs to d. So option 2 is a right option. By maximum modulus principle we can tell, since f is a holomorphic function, on the unit disk and absolute value of fz less than equal to 1, then by maximum modulus principle we can tell absolute value of gz less than equal to 1. But noticeable one thing, this is very interesting. Here given fb and holomorphic function, but not given fb non-constant holomorphic function. By maximum modulus principle, we all of us know, when fb non-constant holomorphic function, then the maximum value exists on the boundary. But here given f is just holomorphic function. If we consider fz equal to half, means constant function, then gz equal to, this value would be half z, and since modulus of z less than 1, that means 1 over modulus of z, this is greater than 1, so this value would greater than 2, half, which is unbounded function. That means we can tell this option is true when f is non-constant holomorphic function, but here given f is only holomorphic function, not given non-constant holomorphic function. So this option also not true. When f is constant, then this value would be unbounded. I hope my all viewers have understood. Next, given G is holomorphic on D, in my previous video I had seen for f prime z, absolute value of f prime z, by Schwarz lemma, modulus of f prime z less than equal to 1 minus absolute value of fz whole square divided by 1 minus absolute value of z whole square. That means from this line we can tell absolute value of f prime z over 1 minus absolute value of fz whole square, this is always less than equal to 1 over 1 minus absolute value of z whole square. and at the point z equal to 0, this value would be absolute value of f prime 0 divided by 1 minus f0 whole square. If we put z equal to 0, that means this value would be less than equal to 1. That implies absolute value of f prime 0 less than equal to 1 minus f0 whole square, and this value is less than equal to 1. So that implies f prime 0, absolute value of f prime 0 less than equal to 1. That means option 4 is a right option. And we cannot tell about a prime z. We cannot tell about a prime z is less than equal to 1 for all z belongs to D if we consider fz equal to 2z, which is holomorphic function, then f prime z would be 2, then modulus of f prime z would be 2, which is greater than 1. So option 3 also wrong option. Only option 4 is a right option. Here only option 4 is a right option because here f0 equal to 0 is not given here. I hope my all viewers have understood. Okay. I will stop here. In my next video, I will discuss different type of singularity. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.